For this video, we're going to be talking about accuracy, precision, and significant figures. You're going to be doing laboratory experiments in this class, and you're going to be looking at data from other people's, labs or measurements as part of your homework. So I'd like to first distinguish the difference between accuracy and precision, and there's a web video that also does this outside of the course. Accuracy is a measure of how close a measurement is to the true value. For example, I have a specific weight. That right now is unknown to me, but I can step on a scale and it will give me a number. Hopefully that number is close to my actual weight. The closer that number is to my actual weight, the more accurate it is. Now the problem is, well, how do we know what the actual weight is without measuring it? Well, that's the difficult part, is often we don't know what the actual weight is or the actual value of some measurement is. All we can do is measure it and hope our measurements come close to the actual value. So accuracy, instead of saying the actual value, it's oftentimes saying the given value. How close are you to the given value? So for example, if I drop an object, it will fall at 9.8 meters per second squared. In lab, we'll be measuring that number. 9.8 meters per second squared is the given number. Your accuracy will be how close are you to that given number. That is different than precision, although colloquially they're often interchanged. Precision is one way of thinking about it that the video will talk about, is how close together your measurements are. But another way of thinking about precision is how many significant digits do you have in your measurement, and we'll talk about significant digits or significant figures in a bit. A scale that measures to the nearest kilogram is less precise than a scale that measures to the nearest gram, which is less precise than the scale that measures to the nearest milligram. So the more precise a measurement is, the more finely tuned that measurement is. Significant figures are a way of communicating to other people how precise your measurements are. When you measure your weight, do you know your weight to the nearest pound, to the nearest gram, to the nearest milligram? When you're measuring the volume of something, are you measuring it in gallons or are you measuring it in milliliters? The two are very different for precision purposes. So significant figures are listed, the rules for significant figures and the definition of what numbers are significant are listed in the unit conversion PDF that made available on the D2L webpage. But we'll go over them very briefly here. So significant figures, all non-zero, numbers are significant. So if I have a number like 123.45, there are 5 significant digits in that number. This number is significant, that number is significant, the 3 is significant, the 4 is significant, and the 5 is significant, having 5 significant figures. If the number has a 0, it becomes a little trickier. For numbers with 0, right? There are 2 parts to this. The first part, A, all zeros between non-zero numbers are significant. For example, the number 101.3 has 4 significant numbers because that 0 is between 2 non-zero numbers. And you don't even have to have a decimal place in there. So 2002, there are still 4 significant digits in that number because those zeros are between non-zero numbers. That's for zeros between non-zero numbers. Alternatively, if the number has a decimal point, the number has a decimal point, all zeros are significant. So for example, the number 2000.0, even though these zeros aren't braced by non-zero numbers, all these zeros are significant because the number has a decimal point. So this number would have 5, 2000.0 would have 5 significant digits. There are some examples that are ambiguous. For example, if I write something like 1200, how many significant digits are in the number 1200? I don't know. According to our rules, these zeros are not between two non-zero numbers, and this number does not have a decimal point. So only the first 2 digits are significant. If I wanted to be explicit and clear that all 4 numbers are significant, there are 2 ways of doing that. The first is writing it in scientific notation. That's writing it in such a way where I place a decimal point after the first number and then multiply it by the appropriate exponent. So 1200 is the same as saying 1.200 times 10 to the 3. Now I've explicitly told you that this number has a decimal point in it. All 4 digits are significant. What if only 3 of them are? What if I know that this 0 is significant, but I don't know if that 0 is significant? Well, I can use scientific notation to write that out. 1.20 times 10 to the 3 makes it clear that there are only 3 significant digits in this number. Now, by significant digit, I mean digits you've actually measured. You have some constraint on. When you step on a bathroom scale, you usually know your weight to the nearest pound or 1/10 of a pound. So you can communicate that with someone by saying, hey, I weigh 130 pounds. But is that 0 significant? Does your bathroom scale actually measure that last digit? It does. So you can either put a decimal after that 0 to show, hey, I know that last number is a 0. It's not a 5 or a 6 or a 7. Now, when you have, all measurements have significant figures. All measurements have some error associated with that measurement. For example, the bathroom scale that reads 130 pounds, if it only reads to the nearest pound, that means there's a ½ a pound error in that measurement. You could be 129.5, or you could be 130.4, or anywhere in between, and the scale would tell you you weigh 130. It rounds. When you combine these measurements with significant errors or significant digits, you have to be careful that your result also is limited by significant digits. And there are 2 easy ways of doing this. The first is multiplication. And again, the rules for adding and subtracting significant digits are on that worksheet. And you might have learned them in a math class as well. For multiplication, so you have 1.02 times 120. You can plug this number into your calculator. 1.02 times 120 gives me 122.4. Now in a math class, you would be done. That's the correct answer. But in a physics or a science class, you have to say, do I really know that this is a 4? Do I really know that this is a 2? Where does my error creep in? Well, the top number has 3 sig figs, 3 significant figures. It has a 0 between 2 non-zero numbers, and there's a decimal point there. Both show that that 0 is significant. The bottom one, there's no decimal point. The bottom one, that 0 is not between 2 non-zero numbers. Therefore, there are only 2 significant figures in the bottom number. Now, when you multiply numbers, your result comes out to be the same number of significant digits as the fewest number of significant digits in the numbers you're multiplying. So since the smallest number of significant digits in the numbers we're multiplying is 2, I have to round this to 2 significant figures. So I would round this to 120. But again, this is a bit ambiguous. Is that 0 significant or not? I know it's not. But I want to be explicit, so I'm going to write it in scientific notation. So it's 1.2 times 10 to the 2. That explicitly states there are only 2 significant digits in my answer. Addition is a little different. For addition, we have to look at the number that's the least precise. For example, 132 plus 1,421.312. Right, so the top one has 3 significant digits, the bottom one has 7, but that's irrelevant because we're adding. We need to look at where's the least precise value for each digit. Well, the least precise value for the top number is the ones place. The least precise value for the bottom number is the tenths, hundredths, the thousandths place. So when we add these together, just doing normal math, use the decimal, so this is still 312. 2 plus 1 is 3. 2 plus 3 is 5. 4 plus 1 is 5. 1 plus nothing is 1. The calculator answer is 1,553.312. However, we have to limit that to a number of significant figures. In this case, we're limited at the ones place. So the ones place is our last significant digit. We don't know what's over here, so we have to round it to the ones place. This rounds down to 1,553. Notice that our result has 4 significant digits in it. The first part of our addition, the first number only had 3. This number had 7. So the number of significant digits in our result has nothing to do with the number of significant figures or significant digits in the numbers we are combining, but it depends on where the precision lays. And this kind of makes sense if you think about it. If you step on a bathroom scale that reads to the nearest pound and someone drops a feather in your hand that weighs only less than a gram, it's not going to change the scale at all. You won't really affect your weight on that threshold. If you were standing on a scale precise enough to measure your weight out to the grams or milligrams, and you drop a feather that weighs a few milligrams, then you would see that recording show up. So that's significant figures, how to add them, how to multiply them, and of course division and subtraction is just very similar, follows the same rules. Division follows the same rules of multiplication, subtraction follows the same rules as addition, and the difference between accuracy and precision.